And you know, everybody, we understand and we have been studying it right from the beginning, that the conservation of mass principle is the most fundamental principles in nature. And it says that mass can never be created nor it can be destroyed. So there are similar laws for similar quantities, and we shall be mentioning it again and again during the course of this work, that is this discussion that is taking place. We are familiar with this principle, and it is not difficult to understand it either. To give you a simple example, if we mix 1 gram of oil with 2 gram of vinegar, then we know how much oil and vinegar are we going to obtain in the form of dressing. So it will be obviously 3 grams. So the mass that is there is to be preserved, and the amount that flows in, that is provided somewhere, should be equal to the mass that flows out. So that is the basic thing, and it can neither be created nor it can be destroyed. That is the basic thing. In a similar manner, another example that we can give is 1 kilogram. If you mix 1 kilogram of oxygen and make it react with 2 kilogram of hydrogens, then we know from the chemistry that we obtain 1 kilogram of water. You will recall that we have the water is indicated in chemistry by H2O. So you can see here that 2 atoms of hydrogen with 1 unit of oxygen combine reacts chemically to form 1 unit of water. And this actually essentially is consistent with the conservation of law of mass conservation. The otherwise, that is, we electrolyze this water that we have made, and then what will happen? Through electrolysis, the water will evaporate, or it will divide itself into hydrogen and oxygen. And again, if we do that, it will separate into 2 kilogram of hydrogen, 1 kilogram of oxygen, verifying that the mass is conserved, mass in is the same as mass out, and it is preserved. And similarly, we can continue with uncountable number of examples. Likewise, another quantity that we deal with is energy. Energy is also a conserved property, and it cannot be created nor it can be destroyed during a certain process. So the same law, the laws of conservation of mass, conservation of momentum, conservation of energy. So similar things are being, however, that it has been found and observed through experiments and with scientific reasoning that although they have to be conserved, they cannot be created, they cannot be destroyed, but they can be converted from one form to another form. That can be done. And that was, first of all, shown by a famous scientist, Albert Einstein, and it is indicated through his famous mathematical equation that he developed, that E is equal to mc square. E is energy, m is the mass, and c is the speed of light in vacuum. So this is a strict condition. If there is no vacuum, then the speed of light could be different. But these are the conditions. So this is how this equation is defined. And what is this gives us? A very simple equation, but it gives us a relation between energy and the mass. And it shows how the two things can be converted from one form to another form. This equation suggests that the mass of a system changes when energy changes. So, however, for all energy interactions encountered in practice, with the exception of nuclear reactions, the change in mass is so little that it can really be ignored. And to give you an example, if 1 kilogram of water is formed from oxygen and hydrogen, when they chemically react with each other, then the amount of energy that is released is about 16,000 kilojoules. And this is equivalent to a change of mass of 1.76 into 10 to power minus 10 kilogram. So, minus 10 kilogram. You can imagine this will be 0, 0, 0, and we continue till these numbers are completed, and then there will be 1, and multiplied by, of course, 1.76. The quantity is so small compared to 1 that if we subtract it, if we add it, it doesn't really make any contribution. So, what do we conclude from that? We can see that the change in mass, if at all there is a change, is so small that it is negligible compared to the other physical quantities that are existing. And the mass is there, this is what is mentioned here. Thus, we have the laws for conservation of mass, a rate of change of mass that is flowing in. This dot normally you will remember from mechanics, solid mechanics, that although dx by dt is a term that we every now and then use in terms of in calculus, but if we have to simply denote it, we show it by dot on the top of the variable that is here, and t is the time with which it is changing. So that shows a rate of change of x, the distance, with respect to time. Here is a rate of change of mass that is flowing in minus the rate of change of mass of the fluid that is flowing out of a given system that is under consideration. And this is denoted by mathematically as derivative of mass within that control volume that is under consideration with respect to the time. So the same thing, and if instead of mass we consider something else, we shall be writing the same thing. Similarly, the laws for conservation of momentum, and that will say that the momentum is conserved, and the laws of conservation of energy, this should be here also as dots, because the rate of change, when it is rate, then there should be dots here.